Problem set 3, question number 6 in cancer screening. So the key to all of these questions was this equation, the kind of colloquially known false positive rate equation or false positive equation. If you remember that, it is 1 minus the false positive rate raised to the power of however many tests or times you're trying to do something. So for part A, we're asking for the probability of at least one false positive given 10 years of annual screening. So if we take this test every year for 10 years, then n equals 10. Our false positive rate was given to us in the question as 0.06, so a 6% false positive rate. If we plug that in, then we get this kind of equation. So 0.94 is the 1 minus 0.06, 1 minus the false positive rate. So we see for part A, 10 years of annual screening, 6% false positive rate. There's a 46% chance of getting at least one false positive. Remember, that's what this equation does. It is at least one of. It doesn't tell us how many, but it is at least one. In part B, we're doing something very similar. In fact, the first part of part B is exactly the same, 0.46. The biannual, instead of 10 years, we're going to take our screening every other year. So there's only going to be 5 of those. We use the exact same kind of formula, only instead of raised to the power of 10, it's raised to the power of 5. And that reduces our probability to 0.27, thereabout. Triannually, we can actually fit in 4 scans in 10 years, so that's the number that should have been used, but I also accepted 3 or 3.33 years. It wasn't important to me to get the number of years strictly correct as it was that you used to this particular equation and used it correctly. So depending if you used 3, 4, or 3.33, you're kind of somewhere in this 20% range. That was good enough for my purposes. In part C, we are still using this equation, but instead of solving for the probability, we are solving for the false positive rate. In fact, perhaps we will change that to probability is equal to 1 minus, etc., etc. So previously we had the false positive, we had n, we wanted p. Well, now, thanks to the literature, we were given a probability of 57% for annual screening, for instance. We were given 10 years of annual screening, and we needed to solve for the false positive rate. So really, it's just some algebra solving for that, and there was a little hint on how to deal with exponents in there. If you were to do that, you get about 8% for annual screening. For the biannual, same kind of thing. P here is equal to 0.36, so 36%. N is 5, because there's the 5 years of biannual screening, and we're still solving for the false positive rate, which is about 0.85. And triannual, again done the same way, with n being either 3, 3.3, or 4, depending how you did it. Is somewhere between 0.07 and 0.095, somewhere kind of around there. Again, the key was just you realizing that every time you need to use this equation, and you're either solving for p or solving for the false positive rate. In theory, you could solve for n, I suppose, but we didn't have to do that. Some of you were rather cleverer than I, and realized that you could use the binomial equation to solve this. I had never really thought about that before. I just defaulted to this equation. But if you think about it, it makes sense. In the binomial equation, you need the probability of an event happening. And we have that. It was a 6% false positive rate. And we needed a number of times that something happened. And that's a little tricky, but we know we want at least one. And we need a fixed number of times that we're going to try and do something. And we had that. So in annual testing for 10 years, we have 10 attempts. So it seems reasonable that we could in fact use the binomial equation. And it turns out that yes, indeed, we can. As alluded to, the tricky part is dealing with the at least one. And so this is the way you would do it using the binomial equation. This part of the equation here, the binom.dist, gives us the probability of no false positives given 10 attempts and a 6% chance of it happening on every attempt. So it's perhaps a little weird thinking, well, why do we care about no attempts? Well, ultimately, what we want is at least one. We have the probability of none, so the complement, 1 minus, the complement of no events is at least 1. So if we calculate the probability of no events and we take the complement, 1 minus, then yea, verily, we get a probability which is the same thing as we would get using the perhaps more complicated false positive rate equation. So well done to those who linked this kind of problem with the binomial equation.